that allows you to put a little bit of sample in, twist it around, get it in the line, and at that point we get a. Thank you. So here, this allows us to get a little bit of a sample in, and then we get the reagents kind of sitting in a tray. So we get in this microchannel, the flow from this channel goes to the intersection, flow from this one goes there. Then we've got the little serpentine in here. What did we do with the serpentine? Who remembers from yesterday? Why did we have those swirly, whirly S channels? Mixer. Yeah, so we want to give our reagents the opportunity to mix. As we spoke through yesterday, mixing in microfluidic systems is really hard because we have low Reynolds number and laminar flow. Think about the windows here. Really nice lecture room to have laminars through. So our flow looks like that. Mixing is really difficult, and that means we need some time to do the mixing. At a certain flow rate, we can increase the time before our detector by increasing the length of the channel. So here we end up with a 25 millimeter channel in a 5 centimeter chip. Then we can see here there's a little detection area where we've got an LED and a laser diode or a photo detector. We're connected with some electronics to get the signal into the computer. If you're not all analytical chemists, and a lot of analytical chemists really love their LEDs because they're a low power using, reasonably narrow wavelength light source that you can quite easily mount under your chip, and you don't need an expensive spectrophotometer. LEDs, you can get them in a whole range of different colors. So if you know the wavelength that your analyte is absorbing at, you can get to a catalog and for $1 or $2 get an LED that matches that spectrum. Then with a photodiode, you can actually measure the current of the amount of light coming through, and very cheaply you can develop your own photo detector. A lot cheaper than what Professor Malik talked about this morning with the UV detectors in HPLC. They've got a multi-wavelength light source where you can select a wavelength. Got really advanced data acquisition in there. Really great, but it's a big box. And for a lot of this work, you actually don't need a lot of wavelength because you know what you're doing, and you only need one. So this one in here is a similar flow injection analysis system, but then a little bit more complex because it's not using one reagent, but a few of them. So here we can see that we've got our carrier, as we had before. We've got our sample, we had that before as well, but we don't have only one reagent, we've got two reagents. And you can see here that we've got a couple of different vials here that contain our sample and our different reagents in the carriers. We've got liquid, we've got valves here that allow us to direct the liquid. And by controlling these valves, we can inject one thing after another, pretty much like a train. So this is the sequence that we want to have. So we start off filling the channel with a little bit of carrier. It comes from here. So all of these valves here are closed. Open that one, carrier gets in front of the train. Then we open our next valve, which is reagent number 2, sitting here. So we then open this one, a little bit of that reagent, we can flow into the channel. We open the next valve, and that way we can put the different liquids in the channel in that order. And we can also make sure they've got good boundaries. As you can see here, our sample is sandwiched between the two reagents that it needs to give its color reaction. Here we've got a familiar feature again, our little serpentine, because we want our sample to be mixed with the two reagents. The reason this sample plug is put in the middle, because there's less distance to mix with both bits of analyte. So these three mix in that serpentine together. You can see it, mixer. And then we've got our LED-based detector that allows us to see an increase in intensity of color with an increase of our analyte. So an analytical technique, it doesn't involve a separation, it's relatively simple. It is based on our analyte giving a particular color reaction when another reagent is present. It shows that we can, by using some valves, we can control the direction, the fluids and the order of with which they are injected into the microchannel. Next separation that Professor Malik mentioned this morning is gas chromatography. Talked about this morning that gas chromatography is different from liquid chromatography because we're talking about gas-based mobile phase and our stationary phase as a solid. Some of the very earliest microfluidic work was trying to do gas chromatography on a chip, and this is a little bit of more advanced. So this is a 2015 example. And what the researchers have done here is, instead of buying a GC column, I'm not sure if you've ever seen one, but they're typically a few silica, a coil of a few silica capillary that looks like kind of a brownish hair that's a couple of meters long and hollow. And the reason that it's a couple of meters long is that they want to have a lot of surface area to allow the analyte to bind and be released or be absorbed and come back. Pretty much like the analytes do in liquid chromatography. Idea of chromatography is the analytes get stuck onto the stationary phase and then released into the mobile phase again. And the more affinity that I've got for the stationary phase, the longer they're stuck on the wall, and therefore the slower the more their retention and the longer it takes for them to be detected. If you've got an analyte that doesn't like the stationary, doesn't have a high affinity for the stationary phase, but likes the mobile phase a lot better, they won't be strongly retained because they spend more time in the mobile phase than they do in the stationary phase, which means that their retention time will be very short and they will come out as first analyte. So here we can see some different, something called the chromatogram that we've seen this morning, where this one's got a slow retention time and comes out rather quickly. This one here is a slow one, so it really likes being stuck to the stationary phase. So that's the way chromatography works. What you need is a lot of surface area to have a lot of parking places for your analytes. So you want to have capacity, you want to have a big parking lot because you've got a lot of analyte molecules and they all want to find their way. To get a proper separation, there are methods to happen just once, but you want to have them come onto the column and get off millions of times, and that's a dynamic equilibrium. Instead of making a really long channel, what this group has done here is they put a lot of posts in the microchannel. So we can see that we've got a 190 micron wide microchannel here, and what they've done is they put a lot of pillars in there. So the pillars are each 20 micron wide. They're all going from the bottom to the top, and that enhances the surface area that we've got. The green here reflects that they have put a coating on there that can act as a stationary phase. So we can see in here that the surface that it's been treated with a group that is designed to interact with the analytes. So what happens here, and it's called a semi-packed column. It's not fully packed because it's not as full as one that's with particles, but it's not an open tubular system either, like the empty capillary that's used in gas chromatography. That's why it's termed a semi-packed column. So we have our analyte mixture is being injected here with a normal off-chip injector as a small injection plug in our carrier. It moves through our column and the analyte sees all the pillars. The analytes that really like our stationary phase, the sticky ones that always stay the last at the party, they spend a lot of time sitting on that pillar. So it gets stuck here, and then it moves a little bit on with the airflow, then it gets stuck here, then it bounces on a little bit more, then it finds a place on the floor to sit. So it's like a group of women shopping. Get stuck at every shop, every window. Then we've got the slowly retained analytes as well. They kind of see the pillars, they don't see the shops, they don't get stuck, they just buzz through. Not sure if you've ever gone shopping with a group of men and women. Quite typically in Australia, the women take ages and the men are out of the shopping street in no time. Chromatography is the same thing. These are the women, these are the men. No bias here, but yeah, I really like that analogy to understand chromatography. The women are just always retained at looking in the shops, and then I've got a pair of jeans, I don't need anything else. So that's how chromatography works. And if with a group you start in a small group at the same point, you actually come out at the other end at different times because you move at different speeds, you've got the same starting point. So the time that you get out is different. And that's why with a detector, we can actually measure the different groups coming out because they come out at their own characteristic time. And here we've got an integrated detector here, where I need to figure out what I need better font here. It was not a FID. Should have written down what the PID detector, that was the one. So it's a detector that works on electrodes and applying a field between these electrodes in the helium carrier. We get an electronic signal in the chip when our analytes come by. So first, our men that are hardly retained, they swim past the detector. The detector says, I measure something, I measure a current. Let's give a peek. And then all the other analytes come past. And here you can see a comparison of the chromatograms, so the electronic trace that you get out of the detector when you send that mixture through a microfabricated column. And here on the right-hand side, it's the left-hand side for you, right-hand side for you watching. Right-hand side, you can see how the same trace looks like in an expensive cubic meter benchtop instrument. You can see the order is the same, peaks are the same. This detector is not quite as sensitive as that one. It's miniaturized, it's fabricated. Can't expect everything, but very comparable separation. We can see the same analytes, we can quantify the same analytes, but here we've done it on a microfluidic device doing gas chromatography and not with an instrument that's sitting on the bench. Liquid chromatography. You're all experts in that. We've done a hands-on session today, we've had a lecture on it, so you all know liquid chromatography. Liquid chromatography was initially tried by Andreas in 1990. Column inlet, realized he needed a lot of capacity, so a very, very long channel going around, a little bit like this one, but then a lot more turns. So remember that one that swirled around? Similar idea. And that's all to get enough capacity in the stationary phase to actually see the difference between the men and women that are shopping. So you need to have enough shops to be able to see the difference. But yeah, this was relatively complex because if you just stuck the stationary phase on the outside of the wall, it was really hard to get sufficient capacity. And therefore people started off packing particles into channels, making little steps in there so that the particles would get nicely stuck, or prepare polymer monoliths. And if you go a little bit further into the chromatography, then you'll know that polymer monoliths are a type of column that you can make. Nice thing about a polymer monolith, it's really porous, so it's very easy to pump liquid through. Doesn't give a lot of back pressure, which means that you don't need a big pump to drive your microchip. Things have progressed, and there is an HPLC chip that's made by Agilent. Yeah, they're still around. So anyone that's ever bought a Hewlett-Packard printer knows that their print cartridges have that polyimide, that brownish material sitting on top. Hewlett-Packard used to own Agilent, and they made both printers and laboratory instrumentation. They heard about all that lab on the chip stuff, and they said, how could we do that with the microfabrication stuff we already got? And they looked at their printers and they thought, we've got polyimide, that's the brown stuff. So they decided to get their chemists to work together with their printing division, and they actually made the microchannels while laser cutting bits of the polyimide. So they used the polyimide that they had in the company anyway for making the printers. They had some experience putting electrodes on there. They knew it was easy to manufacture. They knew they had supply lines in place. And they figured out if you have 3 bits of polyimide, the first one you leave, you don't do anything with. The second one you make, you use a laser cutter to make a structure in. The third one you make some holes in to have excess holes. You then stick them together. You've got a microfluidic device, and we don't need any new infrastructure because we've already been making printers for a very long time. So here you can see the polyimides that they are using for their inkjet print cartridges. What's nice about these devices, so the microfluidic structure is in here. They've got an integrated sprayer tip, so you can connect it directly to the mass spec. And the little points coming out of the polyimide, and if the solvent comes out, this side is grounded, you put the high voltage on the other side. You've got an electro spray interface, so it can the chip can spit its guts straight into the mass spec, so you can do LCMS with them, provided you can do LC on the chip. And Agilent wouldn't be Agilent if they're really good at it. So here's an example of one of the channels, and they pack particles inside the channel, so an integrated LC column. And they've got even a nice enrichment column to do solid phase extraction to concentrate the analytes before they get separated onto the chip. To stop the thing from blocking, there's also a microfilter being put on top where the sample is being injected, because people with mass specs get really iffy if they get particles and other gunk into their mass spec. It's a reasonably expensive box, so you have to forgive them. So the nice part in here, it combines a microfluidic packed column with a rotor and a stator, so things that turn around. And I'm assuming that today with the tour, you've seen how things are injected into the HPLC. You turn the valve around and you redirect the flow paths. Same thing happens here. It interfaces with Agilent pumps and mass specs. The movie we'll be watching is a couple of years old, but all new generations are compatible as well. And it's got enhanced sensitivity compared to nano LCMS. There's also the Agilent Chipmate, which is a competitor. I don't have any shares in Agilent, so if you want to buy another one or work with another one, it's good with me. What I do like about Agilent is that they've got a good movie about what they have, and I hope it's working. There we go. I don't know if the sound is working, but at least the movie, they'll very nicely animate the way that the microfluidic device looks like. It looks like we don't have our funky Agilent music here, but I'll talk you through it. So that's the way the system, a normal, that's the chip system looks like. So the chip will go into that part of the box somewhere. So this is what a normal HPLC looks like. That's the mass spec. And then we've got the box where the chip goes into. It will get better in a second. There we go. So there's the chip. And it's got a nice slot, pretty much like a USB port where you can plug it in. Got a little barcode on there so that the instrument can actually read which one it is, and they can keep track on which chip you used for what separations, which the pharmaceutical industry really likes. And now we go into the detail on this is where it gets more exciting, how the channels actually look like. So that's the sample enrichment column, and there's the packed separation column. And then we go to the polyimide little spray tip that will just electro spray the analytes into the mass spec. It is nice if the music plays in the background, so you may just want to Google Agilent LCMS chip, and then you'll get the funky music with it when you're watching from home. They'll go through an animation with the analytes coming in a little bit, so it's worth waiting. There we go. That's the electrical contacts to activate the electrospray. That's the RF tag that keeps on track which device has been used for bookkeeping in pharmaceutical analysis. I want to go to the inside of the chip. Let's say where. I've lost that part. Looks like it's not doing my favorite part of the movie. Or are we getting there? Maybe we're getting there. Yeah, there we go. There we go. So there we've got the electrospray. I don't think we've seen that this morning. So the electrospray is what you think it is. It sprays. It's just like a garden hose. There we've got the rotor and the stator. I was just too impatient. So very much like the valve you've seen this morning, but then they've got little connection points onto the chip. And then they allow to nicely align. So that happens inside the instrument once you put it in. And then it allows you to have different fluidic pathways. I don't think. So it's working like a 6-point valve, but I don't think you've had that explanation this morning on how you actually the injector works into the LC system. There we go. So this is where the analytes come in. So we've got the sample in, fluidic lines. There's our mixture of different analytes. It's shown as different colored ping pong balls coming in. They go on to the enrichment step. Then they're all enriched from one side of the column and they get eluted in a very small plug into the separation column. You see the shoppers? There's the man, not interested at all. Running to go to the electronic interface, love their computer games. And then they go into the electrospray. So that's how electrospray looks like. Mesmerizing. You get that nice little cone formed. And then it just sprays into the mass. The mass is measured. I think that was the excitement for the afternoon. Yeah, grey box. But yeah, so it shows what's happening with the analytes. It sees them coming onto the column. It shows you how the solid phase extraction works. I like the fact that they revert the flow so that all the analytes are stuck at the front of that column. And then they get out at the back. And you can see them getting separated. So this is a product, I think it's been on the market for 15 years or so. So that's the way that the fluidic pathways are being formed. So that's partially microfabricated, partially not. There we go. It's the liquid pathway pump, first dimension. And it works with a normal HPLC interface, which is all well and good to sell an instrument, but not relevant here. So it's worthwhile watching at that movie a couple of times because I think it also very nicely explains the fundamentals of chromatography because you can see the analytes behaving differently and see how that pre-concentration column actually works. So having the 2 dimensions, one to concentrate all the analytes into a small plug so that you've got very nicely the same starting points and then get them all separated and sprayed into the mass spec. Next analytical technology that I'll very briefly mention it here because I know Phil will be talking about it tomorrow, I think it is. We'll be having a whole lecture on capillary electrophoresis by itself, but as I was going to go through all analytical techniques, I had to mention it. And it's always good to have a little bit of a starter and a heads up to know what's going to happen. So in capillary electrophoresis, we don't have a stationary phase. We separate our men and our women that are slow or fast based on the speed they develop in the electric fields. So rather than being shopping, they're going swimmers, and we've got fast swimmers and slow swimmers. And sometimes they go with the current and sometimes they go against. But their speed is all governed by their how much velocity they can develop in the electric fields, which depends on 2 different things. It depends on how much charge you have, because the more negatively charged you are, the more pressure you have to move towards a positive electrode. So more charge means more speed. But if you're a really tiny agile ion, then you develop a much larger speed than when you're a really bulky protein. Because you get drag in the liquids. I like thinking about molecules as kind of ping pong balls. If you're big, you've got a lot of drag and it's hard to go swim in honey, because remember the first day we're talking about, we're doing low Reynolds number stuff. All your molecules are feeling like they're moving around in honey. So life is not as easy as in a normal cup of water as we leave it. There is a fair bit of resistance to actually move around. The larger the molecule, the more drag there is in the liquid, the slower the velocity that it develops. If you're a small, highly charged ion, you'll be zipping through the system. If you're a big protein with only 1 or 2 positive charges, really that negative electrode is a very long way away, and you only go very, very slowly, like you're a poor swimmer. So we got the small ions, you can see they're moving very quickly towards the, as the cation towards the negative electrodes. The big ones are a bit more slowly, but they all, if you inject them at the same point, they all kind of move together with their analytes of choice, which allows us with a non-selective detector to still tell you who's whom. If you haven't done a lot of analytical chemistry, that may not be obvious either. What we like to do with analytical chemistry is know which peak is what. So what we typically do is that we have standards, and you inject the standard of one analyte only. And if you know that the analyte that you pick comes up here in the fast one comes up after 15 seconds, and you've got a mixture, you know that the one that comes out after 50 seconds was this one, and then the one that came out after 35 seconds was this one. So you first inject all your analytes one after one, and you get a detector signal, and you know analyte 1 comes out at 15, analyte 2 comes out at 23, analyte 4 comes out at 37 seconds. If you then put a mixture in of all 3, you can identify them back, because analytes, if you're a small positively charged ion, you're not going to change that because you're sitting in a mixture. So if you've got a mixture of these analytes, they will always develop the same speed. If you've got the same background electrolytes, same buffer that you're swimming in, and the same potential being applied. So that's the way that we can use an electric signal or a UV absorption signature to still tell different molecular compounds apart. We inject them first, we know what time to expect them. If we've got a mixture, we can trace back who's whom by using the time that they take to migrate. Great thing about capillary electrophoresis, and then Phil will talk to you about more, but the way I like it, it's simple. You just need a buffer, so you need a solution with a couple of salts with a reasonably stable pH and a power supply. No need for pumps and valves. You can just apply your potential difference and go ahead. You don't need have a strong pump, which means that you also can't get leaks. Life gets really easy. The other nice thing about miniaturization that I like for capillary electrophoresis is the resolution that you can achieve is only dependent on the field strength, so the number of volts you apply per centimeter, not on the length line in chromatography. This morning we heard a little bit about resolution, and that's how sharp the peaks are and how much they're spaced. We like really sharp peaks because that means that we can separate more analytes. We get more excited if we can separate 5 than when we can separate 2. And that's why we like high resolution, because that's more likely. The higher our resolution, the more different analytes we can separate in a short period of time. The resolution is limited by the injection length, and that's why we've got a separate session on injection in CE on Monday, where we're talking about how we can inject really small sample plugs into a capillary electrophoresis system on a microchip, because then we can get away with a smaller microchip. There's gated and pinched injections. We'll be going through that. And with capillary electrophoresis, there's a couple of different commercial products on the market, and the number is growing. First one's coming out was GIAN as well. They even launched their CE chip system before they launched their LC system. So there is the GIAN bioanalyzer, which is a fairly nice instrument. Uses square devices that have got 12 samples on there at a time. There's a special kit with a buffer and a gel for DNA, one for RNA and one for protein, and I think there's different sizes as well. All in one system, easy to work. So that system used about 20 micron capillary or microchannels in a glass edge device. They also launched a larger gel-based system. So that's, I think, 500 microns, so about 0.5 millimeter big, which is called a tape station, but it's also part of the microfluidic range. It's used for larger samples, more preparative work for people that are doing a lot of protein. There's also the GIAN chip out there for molecular diagnostics that has licensed and used the same chip. So there's one chip manufacturer that's feeding their chips into 2 microfluidic products. One of the nice things about microfabrication, and that's the last part of this lecture before we go into the detectors, is that with microfabrication you can do things in parallel without a lot more effort. So most devices we've seen so far had one microchannel in there, like the ones here. There's that, yes. So this is a single CE chip. It's got one injection point in there, one separation channel. Depending on how good your computer drawing skills are, so if your computer's drawing skills are reasonably up to scratch, you can actually get exactly the same channel geometry with a bit of fantasy into a very small footprint. So this is what the Matthews group has done, where here you can see the separation channel, where 2 different channels cheaply share a single waste reservoir. And here you can see that they've made the 2 intersections where that one there contains a very simple cross. Here we can see 2 injection crosses that are made. So here we've got one of these crosses. Here we've got the other of the crosses. And that's where the injection takes place. But with the same microfabrication process, but just a slightly different drawing, it's not more effort making a chip like this with, I think this one was 196, this is the 384. So your microfabrication process is exactly the same, doing 1 separation on a chip or doing almost 400 separations on a chip. The voltages here are applied to, so there's an array of electrodes that comes in. Voltages are applied to them all at the same time. And there's a laser scanning underneath here to detect the separations in all the different channels. So nice bit of engineering, but a really nice example on how microfluidic systems, it makes it a lot easier to run a lot of separations in parallel. And one of the nice things is that these high throughput devices are one of the reasons that the Human Genome Project finished in time. So they could use the electrophoresis, but they could go a lot faster, having highly parallel, and then the Human Genome Project got finished. So that's nice. So that was an overview of the separation techniques. I'd say let's take a breather for 5 minutes or so before we move on to the detection system. So slightly different here, but relates to the separations because you need to detect what's coming out of the other end. Unless there's any questions. I'll load my next presentation then. What we got to find this afternoon? You get very tired. I thought we were stopping at 4 every time, and I have 2 presentations left. All good. We do both. And what's the next? We do detection and then workflow. Good. Poor buggers.
You can have the what outside canteen same place.
Yeah, or here. I don't mind. Maybe here is easier.
Okay. Water.
Okay, I'll have a drink now. I gave them 5 minutes, so all good. I know you. Let's just. I'll take a glass of water.
Yes.
See after that.
Yeah, this is
Because then I'd nicely stay on schedule for those that don't mind.
Yeah,
as well.
no.
Yeah. Okay, it's 3. Let's get going. We'll come back again. So we'll be talking now or focusing in on detection. And as you've probably started growing on you, everything we talk about is interconnected. So it's really hard to pull them apart in different lectures. But I've gotten some examples back multiple times to show them so that hopefully it all kind of gels together in your brain. We're now changing gears to detection in microfluidics. And the application that you're using the device for is very important in deciding what kind of detection approach you want to take. There's practical considerations there with your assay. Like, do you want a quantitative or a qualitative answer? Quantitative means that you want to know how much is in there. Qualitative means that you just want to know if it's there or not. Like if you do a COVID test with a lateral flow assay, you're not interested how much COVID you've got. You got it or you don't. A lot of applications where you actually don't care. Like if you're pregnant, you are pregnant or you're not. You can't be 10% pregnant. So there's a lot of applications where quantitation is actually not needed. Whereas there's a lot of applications as well where quantitation is really important because some things are only toxic above a certain level. So your application decides if your detector needs to be able to give you a quantitative answer or if a qualitative answer is good enough. Another consideration is if you want to have your detector sitting on the chip or off the chip, and that typically goes hand in hand with, how portable you want your system to be. If you want your system to be ready to go in a backpack with you to a lake, you probably like your detector to be integrated rather than having a mass spec lugging behind you. Whereas if you want to do your assay somewhere in a diagnostic lab, then you probably don't care as much if you need to carry a separate box for a detector. So again, what you want to do, where you want to use it, will depend how important it is to integrate or not to integrate your detector. And that goes hand in hand with portability. On-chip, off-chip is also a little bit with the detector, like electrode integration, as we'll find out, is quite easy to do. Integration of a mass spec, probably need 15 years and a good team of engineers for that. So yeah, horses for courses, can't say one thing is right, the other one is wrong. It depends on what you want to do. And portability doesn't only come along with a size argument, portability also comes with a power requirement, because quite typically if you go out into the field, you don't have a power socket, so you need to be battery operated. If you want to do more than one analytical run, you probably don't want your detector to be very power hungry. Your decision on detection also depends on what you want to measure. If you want to have an acetate as an analyte, which is not colored, then doing UV absorption detection is probably not the smartest thing to do. So if your analyte doesn't give an optical signal, is not a dye, doesn't have great UV absorbance, doesn't have fluorescence, then you've got two options. Either you give your analytes the properties that you want to use for your detector. A lot of proteins don't. They absorb some UV light, but they're detected by fluorescence detection by sticking a fluorophore to it. And then you can use a fluorescence detector. Another option, if you've got an analyte that's not absorbing any light, is to use indirect detection, which is quite a clever thing. If your analyte doesn't absorb any light, but your background does, as you've seen in those separations, your analytes all cluster together, and they displace the background chemistry, the background electrolyte. So if you've got a background electrolyte that's bright yellow, but your analyte is not, and you measure yellowness, then if your analyte comes past the detector, you get a negative peak. We don't care if our peaks are negative or positive as an analytical chemist, we just like our peaks. So indirect detection, it's typically not as sensitive, but it may be a good option as well if you want to use optical detection, but don't want to go through the pain of labeling your analytes with something colored. The last consideration for your application that's important is, are you actually looking for something that's known, or are you looking for the unknown? A lot of work in proteomics, they have just no idea what they're going to find. So they'd like to have a mass spectrometer, so they can kind of have a very special balance and can measure the mass and therefore identify what was in their sample. Whereas a lot of other assays are, if you want to measure a pesticide that you know is used in a certain region in fruit, you know the pesticide that you're after. So you know your analyte, which then means that your it may not be as critical to have a characterization, structural information coming out of your detector signal. So detection, again, there's a lot of choices. A lot of the decision making will depend on what you want to measure, where you want to measure it, and then what skill do you have. So we've got a whole toolkit, and Professor Malik already went through it a little bit this morning. But if we kind of categorize them, we've got the optical detection techniques, and we've got a lot of them. We've got beautiful detectors sitting in our eyes here. COVID testing, again, we didn't need a detector at home. We just had our eyes and could see positive or negative. Very, very useful way of detecting and reading out an analytical assay. We want to go a little bit more advanced. We can measure the absorbance of light. So we can measure colors, we can measure UV absorption. As we've seen with the flow injection analysis before, if you've got a colored LED and a photodiode detector, you actually already have an absorbance cell, and you can adjust that to different colors. If we want to go more sensitive, but also a little bit more equipment heavy, as we'll see later, can go fluorescence detection. You need to put in a little bit of excitation light, and then you get a whole load of emission light at another wavelength. Really nice. A little bit more funkier, but good for our people that like chemists, is luminescence. May have a reagent that in contact with your analyte produces light. in presence of an electrochemical reaction, and we go electrochemiluminescence. Too complex for me, but a lot of people love it. And then there's spectroscopy. So we already have seen some surface enhanced Raman spectroscopy coming by yesterday, where we had those pillars with the little silver nanoparticles sitting on top. So SPR and SIRS have been done on microfluidic devices as well. I've already kind of alluded to the fact that electrode integration is easy. So electrochemical detection methods are really popular for integration on microfluidic devices as well. We've got conductivity detection. Was very cool when I started my PhD. I was the first one integrating contact and contactless conductivity detection on microfluidic devices. No one remembers, but it was very cool in '99. And then there is the real electrochemical detections, where we can do amperometric or voltammetric detections by applying a potential difference or current to an electrode set relative to a reference, and measuring the oxidation or reduction reactions that are going on in presence of our analytes. And then we've got our special kettle of fish that we've already looked into, where we can do mass spec combined with a chip. There are quartz crystal microbalances, and there's ion mobility spectroscopy that we can do with in combination with chips as well. So I'll talk you through a couple of examples on why things have been done. The first one here is absorption detection. It can be done, but absorption detection is stuck to Beer-Lambert's law. And one of the painful parameters in the Beer-Lambert law is that distance. Microfluidic small distances doesn't really work great. So we've had some people that decided that they wanted to increase the path length, to increase that L, because that makes light look more beautiful. So here you can see a little detection cell where we've got the light here, in this case from an LED, coming in to a mirror, getting a 5 millimeter path length, by putting another mirror in there. So instead of measuring through the silicon 50 micron high channel, so instead of having only a 50 micron path length, by making the structure of this, all of a sudden, you've got 5 millimeter path length, which is half a cuvette. Which then sounds like it's pretty small as well, but a lot of effort being put in. But yeah, absorption detection is great if you've got really bright colors. Path length may a little bit be in your way if you want to do absorption detection in a chip. Then we've had the visual detection, where we've got the color change in presence of an analyte. I see my pictures dropped out here. We'll have lots of colorimetric detection coming on later. Anyone loves optics here? Of course. So, because fluorescence detection, one of the good things about being in microfluidics is that you get to build your own detectors. You don't know anything about optics. You have to put that together. You're like, yeah, cool. Where to start? Start with a lot of money. So what we've got here is a laser and LED as a light source that gets the laser through, focused by a lens. So light always comes work out everywhere, like my laser pointer. Points my laser pointer, if it works. It's really small when I stand close by. If I point at the other wall, dots that I've got gets bigger and bigger, because the light is never nice and small in a circle. So we got a lens here to kind of focus it to a point. Then we've got a pinhole that pretty much makes the circle nice and small again. Then we've got something called a dichroic mirror, and a dichroic mirror sends light from one wavelength in one direction, and so it reflects one wavelength, and it allows another wavelength to get through, and that's why we've got lines going up here. So we've got the light coming in, the excitation wavelength is reflected down here towards our chip, through another collimator lens. Collimator lenses, you just believe that they do what they do with their what's in the box, but they keep the light nice and in a straight line, because we don't want to have a large diffuse detection spot. We want to have it nice and tidy. So light comes from the laser, gets nicely skimmed off by the pinhole, is reflected down into a focusing lens onto a small part of your chip. And if your analyte comes by, there's fluorescence, so there's a fluorescent molecule coming there. Then it drops the light, it says, yay, I emit light. The emitted light is going through the collimator as well, so it gets moved up. It is of a higher wavelength, so this dichroic mirror actually does allow the higher wavelength light to go in a straight line up. Then we've got another 2000 volts of optics before we go to our detector in a nice little circle as well, a nice compact band. So that's a fluorescence detector. And I've tried to get a couple of them commercially available, but from my experience, if you want to do fluorescence detection in microfluidics, it is get friends with the Edmund Optics or whatever the optics companies are, get friendly with the catalog, get a paper in there, realize the parts that you've got to do, be prepared to spend 2 days in the lab aligning all of these things because they all need to be perfectly straight, and then you never touch it ever again. Once it's focused, don't even think about going home. You get a signal, life is good. What other things people have done with optical things, and this is in the hope there's a couple of people that like physics here. So instead of using a detector that comes from external optical components, you can actually use fluids in a microchannel as liquid light guides. No one gets green. So there's different liquids that, depending on their refractive indices, can actually keep light contained as if they're in a channel. And here you can see the light coming in. They've got liquids in here with different refractive indices, which means that we can get the different wavelengths out as well. So there's been a fair bit of work going on with combining optics and microfluidics, up to the point that we've got now a whole new research field that's called optofluidics. That's people that like combining fluidic channels with optical components. Got some excitement there. So in addition to getting your liquids in your microchannels to carry the light, you can also actually buy optical fibers off the market and microfabricate slots in your microchip to get the fibers into your chip so that your light gets really nice and close to your channel. And that's what we can see here on the slide. We can see here a microchannel where we've got 3 different inlets, 1 for our sample, 2 for some sheet fluids. We talked about those curtain flows yesterday. A sheet fluid, make sure that your liquid that you want to see stays really nicely confined in the middle of your channel. For detection, it's nice to be in the middle of the channel and not at the edges, because edges are never perfect and you get reflection of light and disturbance of your detection signal. Nothing. So the sheath fluids there are to make sure we can do optical detection without being bothered by our defects of the fabrication. And what they've done here very cleverly is they, in addition to their microfluidic channel, they made 2 additional microchannels. And those microchannels were exactly the size of the outside of an optical fiber. Then they got someone with really good eyesight and really stable hands, and they got them to poke an optical fiber into a channel the size of a hair, because optical fibers are also about 200 micron. Can be done. So very patient PhD student here poked an optical fiber into a microfabricated structure to end up only microns away from the channel where they want to do the optical measurements. And then there will be another one sitting here on the other side to collect the light coming through. So optical fibers can be integrated into microfluidic devices. If you know how big they are, you can make them part of the design. You can machine your channels for the optical fibers at the same time as you make your fluidics, and you end up with an optofluidic device. Haven't quite warmed up to them yet, but apparently the whispering resonators are really cool in the field of fluidics. And in conference I go to, a lot of people talk about it. They're round thingies, and light keeps on bouncing around and getting more and more energy. If you're into optics, maybe interesting to look at, to see what's going on. Another nice thing is, because we're microfabricating in transparent materials, we can actually make it kind of a dome shape as well. We can fabricate our lenses at the same time as we fabricate our devices. A little bit harder than you think it would be initially, but there's been some really nice successes. Even if you've got just a slightly curved lens sitting next to the channel, that may actually already allow you to focus your light in much smaller dots. And there's some really nice simulation packages in optics that help you determine what the curvature is of the integrated lenses that you want to have. But here you can see a nice round polymer micro lens that has been integrated into a microfluidic device that also contains some electrodes. So optical fibers, micro lenses, whispering gallery resonators, whatever they do, they all can be integrated in microfluidic structures. There's a lot of optical components that are being microfabricated. Their materials are really cool, really close to what can be done with microfluidics. So it's kind of a natural match. We'll have a little bit of a look as well as imaging. I said we were not going to have too much of a concern, too much of a focus on cell culture, but because it's so big, I thought that in today's session about imaging or about detection, we can't just skip over imaging. And imaging can be done in a whole range of different ways. So just a normal bright field microscope, normal or inverted, both work, to have a look to see what's going on with the microscope. The field that's coming up at the moment is doing chemiluminescence, where you've got an array of electrodes in the reagent and you can actually image cells, image special molecules on cells by applying a potential difference and getting a light response if the protein that you were after is present at that position of the cell, and imaging of live cells gets increasingly important. Spectroscopy, so the FTIR, Raman, SPR, SIRS, all have been done in microfluidic devices. And of course, we've got, in addition to our bright field microscope, if we put an excitation and emission filter, a little fluorescence block in our microscope, we can do fluorescence imaging as well. Principle is exactly the same. So the only reason I put in this in is it allows you to understand the confocal system as well. But we've got, again, the light source. We filter the light here as well so that we know we've got a really narrow wavelength band. A beautiful dichroic mirror that reflects first the light down, gets focused onto the substrate, then up to the detector. Setup is exactly the same for a point detector as for an imaging one. Other than if we go really special for the confocal images, then we can also reconstruct a 3D image. So the normal fluorescence microscopy, the difference in Z direction is quite big and you can't quite see, get the Z resolution. The nice thing about confocal microscopy is that you actually do get the Z resolution, but you can scan in the Z direction. And then the images you get out of your confocal microscopy system is three-dimensional, which is really cool if you want to look at how proteins are distributed around a cell. There's a fair bit of work being done with cell imaging, and this here is an example where we've got a microfluidic device made in PDMS. PDMS was that stuff, so the swashy stuff, that's the swashy stuff. So it's a PDMS microchannel where they're culturing some bacteria causing tuberculosis in. And here you can see that they've applied a couple of different stains. And you can see where the fluorophore has attached and where it hasn't, which allows you to do some, it helps the people studying, in this case, tuberculosis, to do their research better, having that all confined in a chamber where you have control over the, for example, the efficacy of antibiotics being added. You can see if they die or not in your fluorescence microscopy images. This here is an overview for you guys to have an idea where there's a whole range of different optical methods, typically done in glass or PDMS, unless you do FTIR, because then you need to have your calcium fluoride as a microfluidic substrate. All of them have their advantages and disadvantages in terms of sensitivity, complexity. But we've got the range of options that are open for detection for large-scale microscopy as well as analytical instrumentation. It's all available for microfluidic systems as well. Changing gears, talked about conductivity detection before. So conductivity detection, not the most complex technique, it measures conductivity or differences in conductivity. So if your analyzed zone has got a different conductivity to your background electrolyte, you get a different detector signal out. And this should have animated. They're now on top of each other. That's not nice. Well, let's just ignore the contact ones because we can't see them anymore. And then, so contact conductivity detection is two electrodes that sit in the fluid and they measure the conductivity between them. One of the problems if you want to use a contact conductivity detection in capillary electrophoresis is that you get a potential drop over the width of your electrode because you've got your separation going in a field gradient. So you get a potential drop from one edge of your electrode to the other. And the real electrochemists here in the room already realized you get trouble because you get electrolysis happening at your electrodes, you get bubbles, and your electrophoresis goes to a place where you don't want to be. So easy to make contact conductivity detectors, not always very practical because you also risk electrode fouling. And therefore, in capillary-based electrophoresis system, people have come up with the idea of contactless conductivity detection, where you either put two rings, you put rings of electrodes around the capillary, with or without a shield. There's a bit of discussion in the literature what's good or not. But what happens is that the walls start acting as a capacitor if you apply an AC signal. And through a circuit, in absence of a ground, it looks like this. In presence of the ground, it looks like this. We can actually see that we've got the fluid resistance, the electrical resistance of our solution in our electrical scheme here. So we've got an AC signal that's applied to the input electrode. We've got the capacitance here in the wall that's just taking a little bit of our signal away. Then we've got the solution of the electrical resistance of our solution that connects the input with the output. And then we can measure, with a lock-in amplifier, we can measure the AC signal coming through the solution into our output electrode. Doing a whole range of signal processing allows us to get back to what our resistance of the solution is. If we get different analytes coming through our detector cell, we can measure that difference in resistance. This is the $20,000 chip that I just told you about that I magically destroyed by just trying to rinse it. There is the little bugger, so it was a 4-electrode system, and these electrodes were actually dug into the ground of the chip and then covered up by an insulating layer. So it was a 21-step microfabrication process to first dig a hole into the microchip. The platinum electrodes don't stick well to glass, so you first need a layer of chromium that sticks to the glass to then allow the platinum electrode to stick to the chromium. That all needs to be leveled off exactly into the little hole that they first dug. Then it needs to be covered up with the silicon nitride, not the silicon oxide layer. And then you can build a microchannel on top and stick them all together. 21-step process, took 3 days and a lot of labor.
Can we take a break?
Yeah.
Because your coffee is getting cold.
Oh, I can also I just drink as we go. Well, that's my next thing that I was going to do anyway, was give you my budget conductivity detector that I sneakily held behind. So this is my old cheapo way of making microfluidic devices with integrated detector. Any of you here that's got a hobby in electronics, made a printed circuit board? So this is just a normal copper printed circuit board where I used a mask to etch and got conductivity detector electrodes in there. I then put some photosensitive material on there to make sure the floor was even, with some holes in there where the electrodes were so that the electrodes wouldn't be sticking out anymore. Then put another layer of photoresist on where I made a channel in, and put a third layer on top to seal the channel. So I did this partially in Tasmania, partially in Peter House's group in 2010. So this probably cost $2. That was my little revenge on that $20,000 chip. Sensitivity is the same, no difference in performance. So it doesn't always need to be expensive and fancy. This one, it looked really nice. It had a bluish glow to it. It was a pretty thing to look at, but that is as effective and a lot cheaper to make, and a lot less waiting around, because that was for me. I just would actually electrode plates in a batch of doing 50 or so at a time, and then making devices with laminated photoresist would be 2 hours of work. So on a normal day, I could just make a device, destroy it, and make a new one. Whereas with these ones, I had to wait 2 weeks. But yeah, it's nice to see the contrast at this point in time. And I'll have something, a little sip of my hot drink. But yeah, if you're interested to do anything microfluidic, have a little bit of a look at what the budget microfabrication approaches are that are available. Because there's actually a lot that's possible without having a clean room facility. Which I haven't asked, do we have a clean room facility here on campus? Can we make chips yet? I don't think so. I've never worked at a university that had, so it's not a requirement for having any kind of success in the field. It's nice to have access. I've had the training, I've been in them. One of the most annoying things, if we're not having a coffee break anyway, if you're in a clean room, you're dressed up. So you wear a mask and hood and everything, so you only see this part of someone's face. Really hard to recognize your colleagues, particularly if you don't know them really well. It's, yeah, if you only see that part, and it's like, whoa, were they tall or not? Which one is my friend to go to now? Or you're all suited up. Thankful as well if you have to go to the toilet because you need to all dress up. Yeah, dress, undress, do the workout on cleaning and processing. But it's good to have been in one. It's good to realize how hard it is to keep a clean environment clean, and how much dust we actually introduce with everything we do. Because any clean room only has got its rating on Monday morning when people haven't been in over the weekend. And other than that, the class 1,000 clean room, so 1,000 clean room, the class 1,000 clean room means that you've got 1,000 particles per cubic meter. It's only there on Monday morning. As soon as people have come in, it's class 10,000, because we just bring a lot of stuff with us, even though we are all count up. That's lovely. Thank you. So we'll be playing around with paper fluidics as well. This is one particle. This is actually a paper by Peter Houser that I did work with. And what they've done here is they combined a conductivity detector that they call here, chemists get funky. So the electrodes, the one that's not in contact is called the capacitively coupled contactless conductivity detector, which is a bit of a pain to say, and that's why we say C4D, because there's 4 words with a C before we say detector. So the C4D sensor here is one of the things you're looking at there. And what they did is they wanted to measure SO2, which was generated from sulfide into food, reacted with some acids, got a gas being formed. The gas penetrated the gas permeable layer to then be wetted in some water again. And then the increase in conductivity could be measured by the C4D detector. The chemical scheme is a little bit more clear in this slide. So you can see the sulfides that could be present in foodstuff because it's used as a preservative, gets in contact with the acidic solution, forms SO2. There's a gas permeable membrane, so the SO2 can permeate through, but the liquids that were present in the microfluidic channel, they can't. having permeated the membrane, it ends up in a water environment again, where it gets back, it reacts with the water to form HSO3 minus, which is an ion and provides conductivity. And you see the contactless conductivity scheme that I just spoke through, sitting as a detector here, where, like the one that you just had through, we've got PCB packaging, we've got the 2 electrodes sitting on top, and we've got the insulating layer sitting on over. So it's pretty much the detector that you've got in your hands there, but instead of having a plastic channel being laminated on top, they put a paper fluidic device on top to be able to measure some preservatives. Published quite recently, 2 years ago, in Sensor and Actuators B. Nice paper. And they got a nice response. So the more sulfides they put in, the bigger the signal is they got, which we always like as analytical chemists. We like things to be linear. We like to be able to quantify, do quantitative measurements by measuring a certain C4D signal and then saying, there was about 70 milligrams per liter of sulfide in that mixture. We like doing that. And we can see that with increasing sulfide levels in the sample, it took a little bit more time for the higher concentrations to get to an equilibrium, because the chemical reaction had to take place, the analyte had to diffuse through the gas permeable membrane, and then dissolve again. So that creates a little bit of a lag time here to get to the full signal intensity. Next one that has been done is electrochemical detection, where there's been amperometry and potentiometry have both been done. One, we apply current, and when we can have an ion selective electrode and measure the potential that's coming up. And the other one, we apply a potential where we get an oxidation or reduction, and we measure the current that's generated in that process. Lots of people have done electrochemical detection. Here, this is an example where they've used Parylene C, which is also a conducting polymer. Can see some really nice microfabricated electrodes. These were people that had access to a very funky clean room. So you can see nice electrodes sitting here, a range of different reagents that can be gone in. And what they did here was a glucose assay. So the difference between a biosensor and an electrochemical detector is having a biorecognition element, which is an enzyme or another molecule. So the way that the glucose assay works is that there's an enzyme that releases some peroxide if it's in contact with glucose, and then it's electrochemically the peroxide is being measured. So there's, in presence of the analyte, there's a biochemical conversion, and the product of that chemical biodiversion is conversion is actually the analyte that's being measured. I thought we had to mention that, but I'm not quite convinced yet. But in addition to microfluidics and a lab on a chip, there's also people that have lab on a thread, where they had take a cotton thread like this, where our clothes are made on. There's small microcontainers as well. You can wet them with electrolytes and move things along. So what they've done here is they started off with a nylon thread. They put a hollow conductive carbon electrode over it, then coated that with molybdenum sulfide, put an aptamer on there. An aptamer is a bit of DNA that thinks it's an antibody. So it's a bit of DNA that's folded in a geometry so that it becomes a recognition element. The part where proteins could be sticking are pre-blocked with BSA, and then we can, with that functionalized carbon electrode, it is actually possible to do electrochemical detection when we've got 3 bits of thread from a bit of fabric sitting together. Fabric by wicking, we know in the washing machine our clothes get wet, so they absorb water. The threads by themselves do that as well. So we can use them as a fluidic vehicle themselves and use them to do bioassays. It's not huge, certainly not as big a field as microfluidics, but it's something that's been around, I think, for now about 10 years, so it's probably there to stay. There's some really nice applications of working with threads, and it's another nice example of a budget way of doing advanced chemical analysis using cheap materials. We'll have a special session on paper microfluidics, but paper microfluidics has also been done with conductivity detector. If you think this looks like origami, it is. It's microfluidic origami. The idea is that we can fold and open things to add reagents together and open them up again. But the important part, why I put a slide in here, this is a typical electrochemical detector. So what they could do here is having the substrate and the enzyme bed sitting next to each other, so they could deposit the reagents. They could fold this over and do an electrochemical assay. And they did this to do a couple of inhibition assays, I think with pesticides. And they could measure the inhibition of the conversion of the substrate by the enzyme electrochemically on top of a carbon black electrodes, sometimes functionalized with nanoparticles, sometimes not, to measure atrazine and others. So this is, a paper fluidic device in order to absorb the analytes and get in a very well-defined, well-confined environment, gets the enzyme and the substrate folded on top of the electrodes. But we'll have a whole session on paper fluidics, and I'm convincing Professor Malik that we actually can do some making of paper fluidic devices ourselves as well. Amperometry with ion selective electrodes can be done with a single ion selective electrode, as we know from our pH meter in the lab. You can also make a whole lot of them, and here we have a nice array of amperometric electrodes where we've started off making a template by a 3D printer, put a membrane in place because we want to do some filter step, pour some PDMS over to make it into silicon rubber, peel that off, then put silver chloride electrode on, do a whole range of other processing to then finally get electrodes in a fluidic device all in one. And then that was combined with some custom developed electronics, which is important. Having friends in electrical engineering is very important. And what they did for this was using ion selective electrodes for the mono's cholesterol, uric acid, cholesterol, lactate, and glucose. So these are the four analytes that were being measured. The researcher here took a mouth swab, eluted it. The sample got fluidically brought in contact with the four different sensors. All these segment sensors, here you can see the calibration data. And here you can see the biomarker profiles of this subject. The nice thing about the microfluidics system is sensors have the problem that they only sense one thing at a time, but the microfluidic system allows you to put four different sensors in parallel, which means that you can measure four biomarkers at the same time. And here you can see that between some different subjects. Electrochemiluminescence, very good word for Scrabble. What happens in electrochemiluminescence is that you get the oxidation of rubidity as well as a co-reactant happening at the same time when potential is applied. The co-reactant then forms a radical in presence of the analyte that then gets the rubidity to generate light, which then can be measured. A lot of electrochemistry going on. The nice thing is that we've thought through our fluorescence detection setup where we needed the dichroic mirrors, focusing lenses, and all of that. You need a lot less optics when you do electrochemiluminescence because you now don't need excitation light because your light comes from an electrochemical reaction. So the detection readout using electrochemiluminescence is a lot less intensive than it is when you do fluorescence detection. And electrochemiluminescence has been used here in parallel in a couple of different microchannels, where again they got a setup here. So they've got a syringe pump that's connected to two different valves to get the sample into three different channels. There's tubings. The microchip contains a top plate that's made out of PMMA. Where are we? There are some electrodes for generating the electrochemiluminescence, a reference electrode because it's electrochemistry. We've got a PDMS substrate here, which has got the microfluidic channels to control the flow. And then we've got a block here that contains an electrode with some hydrophobic barriers to contain the liquid in place. That's got a patch sitting there on the bottom that contains the antibodies as well as the electrochemiluminescence reagents. And this whole system makes then an array of 9 different detector spots. And with those 9 spots, we can, from 3 different samples, measure 3 different lines. Why does it shouldn't be here? See if my next slide is somewhere else. Okay. There should have been a slide here that was not labeled chip LCMS, but one that had a microscope image where you could actually see the chemiluminescence coming from a couple of these different reservoirs. If you look at the paper, you'll be able to find that back. But electrochemiluminescence can be done on microfluidic devices as well. Then we go to the point chip LCMS, we've seen. There's also high pressure mass spectrometry where they reduce the needs for vacuum for the mass spectrometer to open, to be operated, which now gets the first field portable mass spectrometers in place, which is of course interesting to the microfluidics field. And we'll be looking at that a little bit more detail when we talk about proteins. So conclusion, lots of different detectors out there. Pick a detector that suits your preferences, as well as the microfabrication facilities and the application that you've got in need. But yeah, we've got anything there from $5 to 20,000. So the sky's the limit. There's horses for horses, but there's lots of different detectors around. Okay, then we take another couple of minute break and then we'll be going on to the integrated systems. You guys will be tired tonight. We'll take a 5-minute break so that we all hopefully can get home a bit before 5. So these are pretty much the same. This one is mounted on the electrodes for detection. That one is used for Our attendance is being monitored. slowly getting to the point that the unrelated bits of information start getting together.
That's good, that's
Hmm?
pressure.
That's fine. Very understandable. It's a long, long day. I agree. Poor kids have to sit for 3 in a row. It's a tough ask.
We got 10 days already. For 10 days.
Yeah, but
We as a teacher also when we go for the teacher training courses, it is from 9:30 to 4:30.
So only lectures, any test, any MCQ, no?
at the moment, it's, well, I'm hoping with, personally, at the moment, if we can do some hands-on paper with this, it's quite easy to get some crayons and chromatography paper and hot plate. And you can actually make some 2D devices, so I hope we'll be able to have
Yes, it
a little bit of playing around and just jumping and see what's happening.
Yes.
We don't need a lot of infrastructure to have some fun.
Right.
What all we need for this?
Filter paper, crayons, so that the wax, the things kids do coloring with. That's once they're on your floor, you never get them off.
Yes.
And then a hot plate, so what you do is the,
Hot plates?
yeah, so the wax needs to melt into the paper.
Yeah.
And then you create a hydrophobic barrier in the paper, so you have areas that are hydrophilic and you can transfer water. And you've got areas that are hydrophobic because the wax is there,
Okay.
which gets you a hydrophilic system.
But then you have to maintain that wax in a proper temperature?
I've done it at home with my kids at home, at good home. The wax just needs to melt in, so it needs to get a liquid to get through the paper,
Right.
and then you can cool it down again. So, my hot plates at home, my stovetop works, the hot plate in the lab works.
But one can try.
The microwave gets really smelly at home. I've tried my kids using the microwave, that's not a good idea.
Should we want tea?
I've had my tea, that was great, I'm now having a glass of water. But yeah, a lot of things make a lot more sense if you can actually touch and feel them. I'll show you better.
Summer to open, not to leave around.
That shall help. There are 400 micron channels that were 3D printed and then just sticky tape onto the glass slides. It becomes a lot more easier to imagine what you actually hold.
So how long it takes to,
2 hours?
Is we can check the sample.
from here, from the holes?
From the house, so you have to show me the house.
Yeah, from the holes.
The other side will get it.
Well, this is one to do particle separations in, so we, this is the one that we use with the non-Newtonian fluids.
Okay, for the non-Newtonian.
Yeah, so we looked at particle focusing in non-Newtonian fluids, these ones, so we didn't need a detector, we just had a microscope. We had some droplets making, so you can see that there's channels that get together to have a octanol water system, and then you can do liquid extraction in droplets.
That helps you is important.
And then the technology again.
Right, it-
That's really.
So that, and either you have a 3D printer to make them, or there's 3D printing shops as well, where you can just upload your design, and you get them by mail order.
We haven't getting in the department.
They can be contacted for this.
Yes. He's done printing. Is he has designed his own instrument?
So these micro channels are between, they have been pressed between these material, right?
No, they're printed in.
They're printed in.
this is
It's
printed.
complete structure is printed.
Yeah. So you print material except for where you've got the channels and then you've got a voice.
And these are the small channels, I guess?
They're about 500.
Yeah, the spiral ones, no? Right? This one, this one.
Oh, but they are fitting, so they are,
These are channels.
you can put a lure box in there or an HPLC fitting to connect with your pump.
Okay.
So they're just threads. So this. Okay, so we'll start talking about how to miniaturize the analytical systems. I think said we would be starting again. So if we start developing a microfluidic system, and this is probably the only lecture where I have a fair bit of text in there, because I'll be going through some of the learnings of the first bigger commercial successes that came out as fully integrated systems. But we've got a lot of demands from our application. What do we want to use our analytical device for? So what is the kind of sample preparation we need? What is the assay that we want to do? And how do we want to detect? And we need to somehow combine that with a whole range of fluidic design and fluidic control. So the first part of this hour, I'll be talking a little bit on how we control our fluidic systems. And then I'll be going through some information how the Lenders Group have developed a microfluidic device for forensic testing to get the tandem repeats ready in forensics. And they've gone through a couple of design iterations to aid manufacturability. And together it makes a really nice story to start realizing what to think of when you start a project to make sure it gets as close as possible to commercialization in the end. But first we'll be talking about some fluidic control elements. And we've just probably got a review accepted on how you can actually achieve fluidic control, really from an electrical engineering perspective. And we've got in that system, we've got mechanical systems that are quite obvious as an analytical chemist that you need for control. We may need a pump, we may need some valves, we may need some stepper motors to move detectors around or not. But these don't work just by themselves. So they also need electronic systems. If we've got a photo detector in there sitting, we need an analog to digital or digital to analog converter talking with that. We may need some amplifiers to amplify the system already close to the electrodes. We may want to know what our flow rate is, so we may want to have some pressure sensors, flow sensors in there. Could be a potentiometer. So we've got some mechanical systems to get the flow working, some electronic systems that need to work as well. They don't work by themselves, so we need to have a control algorithm saying under what conditions what part of the system does what. And then we need to have a computing system as well that orchestrates whenever these guys go on or off, whatever is happening with the signals coming in from the sensors. So if the pressure is above so many bar, then the pump should be switched off because otherwise my tubing jumps off. That algorithm, if then comes here with the algorithm, the final commands are being given by the computing system, which is stupid by itself. So a little bit of understanding if you work in a microfluidic system on how the electronic part and control works is very useful because quite often you're developing a new system. So you need to build from scratch and actually think about not only the fact that you need a valve, but also how you're going to be operating your valve. Does it need to be switched at a certain time or when a certain pressure is achieved or when a certain amount of color is being produced? And that's the way that the whole system is interacting, and a little bit of understanding of those kind of schemes helps talk with electrical engineers. We've got a range of different pumps available that we can connect to the outside of our microfluidic device. We'll be touching on some integrated pumps, but that's been proven a rather big challenge to integrate a pump into a microfluidic device. So it looks like the majority of the fluid handling that's being done is using external pumps and valves. We've got our well-known and trusted syringe pump. I've got a lot of good things to it, a lot of bad things as well. There are ones that are commercially available, sometimes even with USB operable programmability. There's also cheaper open source methods. There's even STL files that you can download to 3D print your own 3D printing manifold that you can combine with a step motor and some rods to be able to get the fluid to pump through the syringe. Peristaltic pumps are another class of pump. Difference in their operation is that a syringe pump, it's got a little stepper motor that pushes the plunger forward, so you get relatively pulseless flow. Whereas with a peristaltic pump, the roller rotates around. Every time the roller squeezes the liquid together, you get a pulse, and then it relaxes, so you get very pulsative flow. So depending if your application is sensitive to that or not, you may want to pick over the other. If you really don't like to have any kind of pulsative flow going on, the pneumatic systems are really, really smooth because you control the liquid that's sitting in a tube above the liquid. That means that you've got constant pressure, and therefore you get a very nice and stable constant flow rate. You need a fair few solenoid valves though to control a fluidic system that is pneumatic. One of the, so we've got two different ways of controlling our fluidic systems. There is an open loop control where you say, I want 5 microliters a minute. You close your ears and eyes and anything else, and you just hope that a 5 microliter a minute will come out. There's the closed loop systems where you say, I want 5 microliters a minute. It's being put out, it's being measured, and it's being fed back through an electronic loop to say if your 5 microliters a minute is actually being delivered or not. If it's not delivered, then the pump will be set differently to achieve the desired flow rate. So you get more accurate results that way, but you need a little bit of a more complex system, including having a sensor there for your output. If we look at the response time that's coming out with our flow, we have a couple of different parameters that are important to think about if they are important for the assay you're developing, or what is important. So there is, if you switch on the pump, you want to go to a certain steady state value, let's say 5 microliters a minute. You switch your pump on, your pump is all excited and it overshoots. The little bit of overshoot, so the difference between your steady state line and the height of the first peak when the pump fires, oh, sorry, I went too much, that's called the overshoot. Then the pump is regulating back, so you go a little bit under. And then you've got a smaller overshoot and you go again and then you stabilize. For some microfluidic systems, you want to be above your steady state or at your steady state as soon as you can. You don't mind if there's an overshoot, but you want to get as soon as possible to your flow because you don't want any of your analytes disappearing into another channel. For other applications, however, you may be very pressure sensitive. So you want to avoid an overshoot at any cost, which means that you want to have a very slow ramp and then approximate that level with as little as an overshoot as possible. And then on top of that, you've got the pulsative system where this is for a pressure-driven system. If you've got a peristaltic pump, that overshoot happens every time the roller goes around. So you've got lots of pulses in your system. Would be a pain probably for HPLC because you really want to have a constant flow and a constant pressure. If you do flow injection analysis or just adding some reagents, it probably doesn't matter. So again, depending on what you do with your flow, having a large overshoot, having a long settling time may be an issue, may not be an issue. The best performing system that we found in literature doing a very thorough search was the one that we've got cited here. So it was published in the European Physical Journal E of Soft Matter, which was a little pneumatic pump, which had a home-built pressure regulator in there that was then connected to fluidic solenoid valves before being connected to the fluidic system. And that allowed for the most accurate flow control and the most stable flow. So the syringe pump doesn't have as much pulsing as a peristaltic pump has, but because it's a stepper motor, there is still some movement in there. And another problem with the syringe pump is it builds up a pressure. That pressure doesn't disappear when you switch off the pump. So stopping of syringe pump doesn't mean your flow stops. Your flow only stops when the pressure has been dissipated, which could easily be 5 minutes. So a syringe pump is very easy to program, but be mindful that while you think you set a flow rate, if you've got a lot of back pressure, your chip is blocked, your stepper motor is not really intelligent, so it just keeps on moving and building up the pressure and changing your flow. So it's not always the most ideal pumping platform. So pneumatic systems, if you want to have really smooth flow, are good, but befriend a good electrical engineer because the commercial systems are $15,000 per channel. So a good pneumatic control system, buying them off the shelf is expensive, but with some flow sensors and understanding what you want to achieve, home-built systems are good, and there's a growing number of open source systems available where people have done it before. So if we talk about our microfluidic modes of transport, and this is a very nice paper to be reading. So it came out of the Landers group, and most of the rest of this lecture will be coming from that paper, because what the Landers group has done is that they started, probably around 2001, 2002, it was really cool to do DNA separations, DNA gel electrophoresis on a chip. And then people started dreaming that they wanted to have a field portable forensic system. And since then, they've been churning through millions and millions of research funding, getting an approved forensic analysis system to detect tandem repeats in people's DNA. And it's those tandem repeats that allow forensic people to tell people apart from one and another. So they're, for example, used for as evidence in rape crime. So they get DNA sample of the perpetrator, and if the DNA profile, the tandem repeats of the perpetrator match that of the suspect, then it's a pretty clear-cut case, and the person will go to prison. We've got a fair few options in microfluidics to pick for our fluidic transport. They're sorted alphabetically here, so not quite in order of reference, but we've got acoustic systems where we can use sound waves to move particles, and if we move particles, they directly grid along, and we can therefore use acoustic waves. We can use sound to move liquids around. We can do things by capillary forces, capillary actions like the wicking of paper that we'll be seeing later on. I think this was the lecture when I went over time that you got spared a whole range of physics. But capillary forces, we've all used a straw to have a drink. You know that the liquid is creeping up to the sides of the straw. You can fill capillary forces, you can fill a microchannel with it. So capillary forces are really good to get your channels filled with liquid, get them primed, provided if you're working with water, hydrophilic surface. We'll have spending a little bit of time on centrifugal forces, which is really cool, because if you get a disc spinning, gravity pushes you to the outside, and you can use that to control liquids, because the forces change depending on your spinning speed, which gives you control to move from one chamber to another. A little bit early to have on the list now, but tomorrow Phil will be talking with great delight about the electroosmotic flow, which allows us to move liquids electrokinetically. Get you prepared. The electroosmotic flow is a flow that's driven by the ions that are kind of mobile, sitting at a charged surface wall. So you get the liquid to be flowing, driven from the wall, which is the only flow in the world that's actually square and not parabolic, like all the flow profiles that we know. But I'll leave Phil to tell you a lot more about that. And then there's the pneumatic systems where, as I just showed you, they give very nice smooth flow. We have a reservoir. We control the pressure that's sitting above the liquid, of the air sitting above the liquid. We have a tube sitting down in the bottom of the liquid. And depending on the pressure that we apply above the liquid, we get a flow through the tubing. So you can see those sitting there. In addition to that, we've got the hydrostatic pumps that we just went through the slide that Suleiman made. And we've got simple, humble gravity as well. If we just make sure our liquid levels at the inlet are higher than at the outlet, we will get a flow. I've said before that that could be undesirable. It's actually quite an effective way of pumping as well. If you just want to have, for example, when you're doing cell culture, you just want to have a gentle flow over your cells to perfuse them with fresh medium and to remove any metabolites and other waste products that the cells produce. Actually, gravity-fed systems are really good, particularly if you want to have your cells sitting in an incubator, because no one is happy if you want to put a pump into a big incubator that looks like an oven. So pneumatic valves have been used frequently for in the macro scale, controlling water, having pneumatic tubes where people used to be sending the mail around, logics. They are used at the micro scale as well. Started off with Stephen Quake. We'll have a picture of that on the next slide. But these micro valves allow us to do microfluidic control as well. A very famous paper, and I think Stephen Quake is the only person who got a valve named to him. So a Quake valve has become a term in microfluidics. And what a Quake valve is, it's a two-layer microfluidic system. One of the fluidic lines has got a liquid in there. The other one has got a gas in there. So you can see here, fluid in, air in and out. So we've got this system here filled with liquid. Here we've got air that can go in and out. And what happens is if we increase the air in, we increase the pressure, which means that the bottom of this channel blows up like a balloon. It's an elastomer. We've had the PDMS device, you can feel it, it's kind of soft. If you've got PDMS that's only 50 micron thick, it works like a balloon. So you increase the pressure here, the material, the balloon inflates, and it closes the channel that sits underneath. If you put 3 in a row, you get this one to go down, that one to go down, that one to go down. Keep going, and you've got a peristaltic pump. So you can use it to stop liquid flowing from one point to another. You can also use the Quake valves as a pump. Some people realize that the Quake valve's got the problem that the valve is it's a normally open valve that only gets closed when activated. You can also do it the other way around, that it becomes a normally closed valve that only opens when activated, and that then becomes important if you want to save some energy. So there's a whole range of different active valves that you could think of. We've talked about pneumatic ones. We've got electric ones that we can control with a field. We've got magnetic ones that we can see down here that we can activate using a magnet. We've got thermal valves like a bimetal that moves around whenever they are thermally activated. There's a passive approach as well. We'll be looking in a little bit on some centrifugal devices, but also the devices using the capillarity to control the flows in the microfluidic channels. Hydrophobic patches are really useful because these, the flow in a microfluidic system, the pressure you need to overcome to progress in a channel depends on the wetting. So we just spoke about capillarity and the fact that liquid wets a glass capillary or a glass microchannel by itself. If you functionalize a little ring to make it hydrophobic, then all of a sudden the pressure that you need to overcome increases and your liquid doesn't want to wet the walls anymore. So you stop your driving force of your liquid to go through your channel, And you can stop your flow by having a hydrophobic patch up to the point you overcome that pressure using an external pulse or by dissolving the hydrophobic patch, and then your liquid continues to move again. So the hydrophobic valves are really popular to control the flow or time different events in single-use devices, because once they're primed, they're not useful anymore, but they're really great for using capillarity. If you want to have reagents sequentially being added, you can use a hydrophobic valve and hydrophobic patches to stop flows up to the point you want them to be reactivated again. So the lap on the disc system and centrifugal systems are very popular as well. And they've got their own collection of different valves. So there are capillary valves where we've got a spinning disc and the flow wants to go out. And it's the arrow that we've got here. The capillary valve is based on a sudden expansion. So we can see an expansion of the microchannel here. And the flow coming down here stops and needs a higher pressure to overcome to be able to fill this wider channel. With a rotating disc, you can overcome that pressure by accelerating. But that means that if you start spinning at a slow speed, the flow stops here. You can wait some time for your reagents to dissolve or whatever. You increase your spinning speed, which means that you increase your gravitational force and your liquid will be going further down. A little bit higher pressure, you can realize depositing a hydrophobic patch. Fairly similar response or effect. At a low spin speed, your liquid will stop. You need to spin a lot faster to overcome that pressure and actually go around. The siphon valve is quite interesting as well. So at a certain part, the liquid is being pinned and stays there because there's a back pressure coming from the top, so your liquid gets stuck. You can see if you're spinning at a certain level, it doesn't want to go against the force any further because the force goes from the spinning fields comes down. If you go any faster, you push any harder here, then all of a sudden you may want to overcome that. You may be able to overcome that pressure and allow for the emptying of one reservoir into the other. The last one that's on the picture there are the sacrificial valves, where I really like the example where you just dry in some sugar. Initially, the sugar forms an impermeable barrier, but the more water you've got, the easier the sugar dissolves. And after a little while, your valve just disappears and your liquid can get through. Other examples of sacrificial valves are wax materials that you can melt away with a little shoot of laser. So you've got a wax plug sitting in your microchannel, stopping any flow because it's hydrophobic. You heat the wax with a laser, it melts, it disappears, and your liquid has got the right way to go. So we may have very different requirements for what was my next thing? For sample preparation, DSA, and detection. We also need to think about manufacturing, where we've got two basic considerations to start off with. What material do we want to put it in? Does it need to be transparent? Does it need to be a thermal conductor? And the scalability of the manufacturing. If you're really early stage research, your manufacturing method probably doesn't really matter yet because you just want to see if an assay has got any chance of working. So anything you've got sitting around in the lab will probably do. And it's only once you've got your early data and you think I'm onto a winner here, that a serious consideration about scalability of manufacturing is important. But don't wait too long, because a lot of people really liked PDMS materials being made in the lab because they're not that hard to make, they're easy to replicate, and it's cheap to do in a research lab. Problem with the casting of PDMS, and we'll go through the manufacturing early next week, is that it's a manual process, so it's not easy to automate, which means that the manufacturing is not scalable. It's fine for use 10, 20 devices on the lab bench. If you really want to come up with a commercial winner where you want to sell 100,000, good luck finding someone that wants to cast 1,000 chips, put them in the oven, cut them to size, peel them, So it's not a scalable manufacturing approach. And the closer you get to commercial value, the more important scalable manufacturing becomes. Because if you want to sell your product, it needs to be made somehow. So how do we design chips? Most of the time it starts on a bit of paper in the tea room with a rough design and would this work? Then you talk to an engineer, or I'm not an engineer, so I talk to an engineer. And then they always want dimensions. How big? No idea, 2 centimeters, 3 centimeters, do something. But that's when you start going to the CAD drawings or SolidWorks, where you actually get your dimensions all accurately defined. And then questions come up like the intersections, connections. Do we want straight angles? Can our manufacturer approach make straight angles? Are we better off having rounded corners because square corners are good bubble traps? So is our assay sensitive for bubbles? Then maybe we don't want a really square corner because a bubble will always be sitting there where you want to look at your assay. So is it important what your channel looks like? Do you want to have a square channel? Do you want to have a rectangle? Do you want to have a circle? A triangle? Sky's the limit. So in the design phase, once you're two-dimensional on paper or just looking at length, life is easy. If you start thinking three-dimensional, a lot of questions come up where some of them you'll know the answer, some of them you've got no idea. Still a big find in the literature for capillary electrophoresis. Is round better than square? No one has been able to prove it. So it is, geometry is important, but also don't get too stuck to it because liquids at a certain point don't really care. So 2D drawing, 2D thinking is relatively easy. We talked about seeing the microfluidic circuits as an electronic circuit. So hydrodynamic resistance is a nice way to try to keep your channels all the same length. And that's a nice thing about all the computer-based drawing programs. They actually can calculate the length of a channel, even if it's got a lot of weird curves and things in it. Serpentines are really good because they save your footprint, and most chips get more expensive the bigger they get. There's very few people that are pleased if you ask them for a 30 centimeter channel, 30 centimeters, about that. Because typically in a clean room, wafers don't get beyond 10 centimeters. Getting something micro machined at 30 centimeter scale is not straightforward. So people will be appreciative if you kind of stay the size of a credit card. Seems to be a lot of chips seem to be fitting a credit card. For chambers, it is important to think how they're being filled and emptied. A square chamber with an inlet and an outlet, you always get dead corners. So there's nice designs out in the literature of flow distributors, which a channel splits out as kind of a range of different fingers to fill a chamber from different filling points. Then again, at the outlet, it does the same. So it gets much smoother flow, much more homogeneous flow around the chamber. Be mindful where you put your fluidic connections. There's my little box here. If we look at this one again, see how small the channels are and how big the reservoirs. A lot of your real estate on your chip will be taken by your connectors. So make sure you don't have your channels too close together because your plumbing becomes a nightmare because you're there with the super glue trying to put bits of tubing next to each other and then they push each other off. So the channels are not the only thing to think of. You need to have interface somehow your microfluidic device with the world. The connectors to do that interfacing are big. You're talking about a 50 micron channel and a 5 millimeter fitting. Your fitting is going to be way dominating what you do and not your microchannel. So a lot of real estate will be taken by your fittings. If you want to put a detector in place, try to put a microscope objective in a microchannel. Most of your real estate, you pretty much have space for your connectors, for your microscope objective, and that's your whole chip done. 3D design, and yeah, you're a lot younger than I am, but from my experience, people really struggle to think three-dimensionally. We can quickly draw a chip how it wants to look like two-dimensional on paper. having things sitting on top of each other becomes really complex in our thinking. How do we have wires connecting up and down? How very few people have actually, even with 3D printing, gone diagonally. That seems to be a scary thing. We don't do that in our lives. So most 3D printed devices, and I really dislike that are out in literature actually have 2D design, so they're 2.5 dimensional. People haven't really ventured. We've got the freedom of a third dimension. We haven't really used it yet. But at the same time, layering can save space, but it also complicates imaging, because in some of the spiral devices we tried to get a second dimension and a second layer on there, but it's really hard to start thinking where your microscope objective needs to focus to see what's happening in layer 2 and not in layer 3. So yeah, 3-dimensionality is great, but you need to really know what you're doing. So we're now on to the little talk through on the learnings done in developing an approved system for forensic detection. So in the forensic workflow, there's pre-processing done in the lab. So a crime has been committed, the forensic team comes in. They collect the sample, look at serologies, look what it is it semen, is it blood, is it tears, is it just rainwater? There's some pre-processing taking place where the microfluidic device won't have any influence in. After that, an extract of whatever samples they collected makes it to a genetic laboratory, which then gets us to the workflow we'd like to implement on the microfluidic device. Which means that somehow we want to extract the DNA, kind of roughly know how much it is, then amplify it, then do an electrophoresis assay to get the DNA fragments to indicate where the 10 number repeats are, because that's the part that we use for identification. And then we get the interpretation and we can get confirmation who has committed the crime. So a whole range of different steps that all need to be gelled together. There are very different perspectives, which is something that a lot of researchers that are all ambitious, philanthropic, not caring about money, not really thinking about. So they should be designed by multidisciplinary teams with the end user in mind. It means that you rarely develop a microfluidic device by yourself. It's a team, so you probably have some biologists, biochemists, some people that know the application, engineers, mechatronics, physics. They all need to work together and all understand and appreciate each other's contribution to get to the right results. For the end user, the forensic person that's going to be using the instrument, they don't care. For them, it's just a box. And that box should be safe to work with and make their life easier. They don't care about the technology, they don't even want to know about the technology. Really frustrating if you've got them around the table and you've got a very exciting discussion about your design and they say, I don't care, it just needs to be easy. Then we've got the problem that this person is not going to be paying for the instrument. There's a decision maker sitting above them and they just want it to be faster, better, and cheaper than what they already have in place. So the team that's developing here needs to realize that person needs to be happy, because otherwise they're only going to be selling one because they're going to be complaining. But you also need to meet the requirements of the person that finally needs to put the dollars or the rupees on the table. If you can't convince this person to pay it, that person is never going to get it. You don't even need to start making. Very hard real world there. Very few scientists that actually buy the instrument. So you need to, once you start pitching a research project for commercial development, you end up with some really tough discussions. We thought we'd found a great chip to help with sepsis treatment, and we're looking for funding to develop it any further. Then the people that had some insurance on their panel, the investments, the angel investors said, yeah, but we don't care. In the hospital system, it's much cheaper if the patient dies than when we have to treat them for 3 weeks after. 3 weeks of treatment is a lot more expensive, especially if they develop disabilities later on, Then when they just die, it's a once-off payoff, we write them off, it's done. That was a very big disappointment. We thought we're going to save lives. No funder is interested in saving lives if it may mean that they may have a big health bill by being saved. So understanding that person may have to change your arguments while you're selling that whatever you've got invented is great. The theory of microfluidic devices that I've been happily selling you now is all great. We've got reduced volumes, we've got increased surface to volume ratios. We have faster analysis time, we've got increased sensitivity, smaller footprints, all for lower cost and at a great scale. Additionally, we have more rapid heating and therefore decreasing the reaction times. And we can get enhanced assay sensitivity, minimizing the process in the workflow, and particularly when exposure to harsh conditions or cross-contamination on site is detrimental. Who wouldn't be putting money in there? People have been screaming this since 1990, and there's still very few systems out there. So we get small, that's the last argument. There are a lot of hurdles on the way. It is actually really, really hard to get a microfluidic system from the lab out to the market. Usually it's the academics that come up with the great ideas. They don't quite understand the professionals like me. I thought it was great to save lives and not that there was a big bill if people need to be treated in hospital. That disconnect is really a problem because we as academics believe we've got the best thing on earth, and someone that needs to put the money on the table says, no. There is a general scarcity of functional, manufacturable, fully integrated systems. The DNA forensic system is kind of close, but the sample prep is not fully integrated. And it only has got a very limited scope for application. So despite years and years of development, there is not a lot out there. One of the problems is we're academics. We like our freedom. We like to do it our way. I like square channels. You like round, so I'm different to you. I'm not better, but I'm different. Which means that we don't use the same interface. Microfluidics is really the field where there's no standardization. We've seen the problem with the phones. An iPhone's got a different plug to an Android. I think we're finally getting away from that one. But in electronics, we've got a lot of standardization. Microfluidics isn't there yet. Everybody does it their way. I like a cross with 2 centimeter arms. I like it with 3, which means that we all get different sizes chips. We all do it our own way because that's the way that our supervisor told us. So we've got different inheritance of how things are done, and they're not compatible anywhere where you go. So we have a little bit of a problem that commercialization often fails because products were not designed with commercialization in mind. And the researchers didn't consider or even were aware of compatibility with the infrastructure the chip had to work with in the lab where it was going to be used. It worked fine in my lab because I've got a so many G centrifuge. Unfortunately, the application lab didn't have a centrifuge. Workflow gone. So integrating the entire workflow into a miniaturized total analysis system is great. It's a lovely ambition to have, but the world has come to the realization that there's some things that are just easier done off chip manually or only be integrated in later in life. So maybe we need to get a simple system robust enough to get onto the market first, and then add on to that. For a long time, we've been very ambitious and we want to do the whole world. It is really hard. Every step exponentially increases the complexity of the manufacturing, of the operation. It increases the risk of failure, and that makes life really hard. So if you're going down the way of getting a whole assay, decide on a way to control your fluid, and pneumatic is not better than centrifugal. Decide on something and make sure that all the different parts of your module are done the same way. You can't have a coherent sample in answer out device when module 1 is using a centrifugal force and needs a spinning disc. Number 2 uses part 2 needs a peristaltic pump, and the 4th part uses an electrokinetic system. Stick to a fluid handling platform and all the modules you develop use that fluid handling platform. Otherwise, you're never going to be able to tie them together. Select a versatile and affordable fabrication material. Doesn't really matter if it's glass or a polymer or PDMS, or I'd stir away from PDMS, but make something, again, all your modules, all your little parts that you develop, make sure they're in the same material. That allows you to connect the different modular components, because we've all started having 7 steps on one chip and trying to do all at once. Our little brains are just not smart enough to do sample treatment, separation, detection, all in one go. We need to do it one step at a time, have the modules optimized, and then put them together. And think early about interfacing with the support instruments. Talk with the electrical engineers early, so that you know if you need what you need to have in place there as well. Chip-to-world interfacing is hard, because in all reality, we've all done our COVID tests. Once you've got a swap, you've got about 500 microliters of solution, which is huge for a microfluidic device. So we've got an incompatibility in volumes there. This review was about forensic perpetrators. So what the standard routine is that they wash the outside of a condom to collect genetic material. You don't do that with 10 microliters. You don't do that with nanoliters. You're talking about milliliters volume. It's really hard to interface those kind of samples that you have to deal with the microfluidic world. So how to deal with large samples? Ideally, you've got some pre-concentration system in place that you can pass a lot of sample over and then only get a small amount in your microfluidic device. Or have some millifluidic systems to interface with your microfluidics, so that you have some interface to go from the milliliter scale to the nanoliter scale. Practically, it will be probably a 2-step process, where the sample processing is being done on a much larger scale than the DNA extraction, separation, and then the extraction, the amplification, and the analysis. Sample preparation continues to be hard, particularly when you don't know what sample, if there's going to be mud in there. There's a whole range of different complex samples. And there's a whole industry that has already developed kits for that. So it's particularly for the forensic area. Maybe it actually is smarter to use the in-field sample prep kits that are already available, rather than developing a microfluidic alternative to them. There are some niches left. As we've seen with the blotting chip from Amy Hur, there's ways where you can do a 2-step lysis on a single cell level and get the nuclear material separated from the other material. So you can do multiple step lysis there as well, to first lyse epithelial cells and then only lyse the sperm cells, and that allows you to most likely separate the epithelial cells that come from the person that's been raped and the sperm cell that come from the rapist. Microfluidic affinity sorting has also been really good in just testing the sperm and finding that for forensic purposes. We've looked at the hydrodynamic sorting with the H filter. For amplification, we've got a special session on DNA. So PCR is the polymerase chain reaction, requires thermocycling. There's a couple of different ways that's been done. Different commercial instruments actually use different approaches, but most popular are the ones that are based on a chamber where a heater ramps up and down, rather than having a sample, the PCR sample circulating, flowing over electrodes with different thermal zones. Both have been done, both work, but the chamber-based are by way most popular. Other thing with PCR is that we've got the chemicals that we need to be keeping in mind, and they need to be added. And we've got the biological part where we need to have the Taq polymerase to actually amplify the DNA. Cold chain storage is, I think, a word that I hadn't realized up to the point the problems with the PCR testing across the country for COVID came up and why the lateral flow assays became so important. Tech polymerase needs to be, if it's wet, it needs to be staying cool, which means that it can only be transported in cooled trucks, which means that it's really hard to get to the non-urban areas. Avoidance of cold chain storage is really important if you want to get to field portable instrumentation. How you can do that is use lyophilized or dehydrated reagents in your chip that you only wet before you use that. May need some fluidics and some complexities to actually get them reconstituted, but it's worth it for the usability of your device if you don't need to store your device in a fridge. So the very first device, and I like putting this in because I told you that James started doing his gel electrophoresis. Pretty sure I saw him doing gel electrophoresis in 2001. They made it to an integrated device in 2006. So this is the Landers Group, PNS, great journal. We thought as a community, we're almost there to do complete STR profiling on the chip. So we've got the yellow part here, which are doing the DNA extraction. So it's got a solid phase packed column in there to do solid phase extraction of DNA. Then we had some fluids handling. So after the PCR reagents were sitting here, so the PCR, so we got solid phase extraction. Then we got amplification of our PCR products. Then we get a cross injection here. We've just talked a little about CE, so you can see a little cross injection here. So we get gel electrophoresis being done there. So we thought as a community, we've done well. Andreas Hans came up in 1990 with a micropress concept. Look, James, 2006. He's got it all on a chip. We're good to go. We're going to have, before it's 2010, we'll have a forensic DNA analysis system. We're doing great as a community. And it worked in the lab. And then manufacturability came in. And then they found out that this hot embossed cartridge was not really easy. And then they started thinking about their fluid handling and how big the pumps were that they had. And then they sat in a corner and they cried really loud. And then they realized that maybe centrifugal systems are actually better than pump-driven systems, so they had to redesign everything. Went to a centrifugal platform because they couldn't get the pumps combined with a microfluidic system in a way that economically made sense. So they then moved to a centrifugal device where here we've got a system to do the electrophoresis. So this is a commercial system, so the whole system is not out in literature. There's two different bits there. So here we've got a centrifugal system where, again, we've got our separation chip, where we've got our channel, separation channel for the CE here and there. They use some gold leaf that you make use to put on wishing cards for people. They figured out you can also rub them off and make them the electrodes for doing CE separation. The nice thing about this chip is that it can actually fill itself with the background electrolyte for electrophoretic separation using the rotation of the disc after they've popped a hydrophobic valve with a laser. So technically exactly the same separation conditions as they use here. What they've won is A, they've got integrated electrodes, and B, they've got their fluidic control sorted by a spinning disc, which then interfaces with the other thing that I've done. This is a sample preparation where they realize solid phase extraction is hard because you need to pack beads into a microfluidic device, which is painful, it's time consuming, it's got a high failure rate. So they've developed an enzyme cocktail that can do the lysis and the DNA cleanup by itself. So again, this is a spinning disc, so no pump needed. It's rotating around with gravitational force, it's driving the liquid movement. There is a sample that's being collected on a set of nanoparticles. After you spin it a little bit louder, a little bit harder, one of the valves is opened, and you get the red liquid to be moved to the waste. So first, that one is being popped, the red liquid can go down. Then that one is getting popped, the liquid gets spun to waste because the particles that sit there collects in this case it's COVID, so collect the viral sample. Then the magic lysis buffer comes in, lyses the viral particles that have been collected there. They're magnetic particles, so a little bit of an electromagnet sitting under the spinning disk allows for the agitation. And then it's all eluted after popping the next valve with the laser. And then it's ready to be introduced in the other spinning disk to do the amplification and the detection. So I think this system through GIAN was FDA approved in 2019 or 2020. So it took a complete re-engineering of the system. Parts of the chemistry had to be revisited. In 2006, everybody was convinced we're almost there. No, because James hadn't, like the whole community, no one had gone this far before. So no one had realized that actually having pumps is a pain and it's making it really expensive. It requires really complex control systems. We have to go centrifugal to make it fit the budget. And there's still a lot of limitations with the system that I finally ended up with. So don't expect too much. Be modest in setting your scope. Don't say you'll do any DNA containing sample in any forensic scenario. Focus maybe just on the condom outside wash. Pick a very specific application and don't think too broad too quickly, because you can't do it all in one go. So what they realized is that they really had to narrow their scope. There were some requirements for certain uses for legal reasons that would be getting better sales. So to have the PCR amplification quantitative, you need to pre-quantify the DNA before you amplify it to know how much reagent to add. They've let that go. They said, well, we're just not going to meet that now. Maybe we can add that fluidic handling now, but let's first get a system to the market. We're not going to be able to solve all problems in one go. So miniaturizing of the workflow, it's hard because it combines all the different elements. There's the physics, there's the control elements, there is the manufacturing aspects, there is the functional complexity, and we'll be talking about functional integration a little bit later. The microfluidic chip shop, and I really like that example before I go home. A simple chip made by injection molding at a chip shop costs $50. If you want to have 2 electrodes in there, the price goes up to $150. So it goes times three, because you've got integrated electrodes. If you want to have the same chip with electrodes and a membrane, it's $600. So the price goes up exponentially the more different functionalities you want to have integrated. And the reason is that is because even at a commercial scale, the success rate of manufacturing drops drastically the more functionalities we've got integrated. So simplicity, modesty is very important. The sky is the limit, but it will bite you in the bum. Easy is better. We've made it through the day. Any questions? Yes, you can go home. Let me know if there's anything you want to know more about, do different. Otherwise, have a good rest. And then we'll have another day of fun, and hopefully things will be getting together by tomorrow. I'm hopeful. I'm an optimist. I was convinced James was going to be there in 2008. He was too. He's been a very grumpy man for years. I think he's been grumpy. He only got less grumpy again around 2015, 16, when he could see that the centrifugal thing was actually going to make the real market, because it's getting something that actually is going to make money is really, really hard. So if someone offers you a course in commercialization, even though you think as a ambitious scientist, money is dirty, it actually doesn't hurt to learn about both IP, but also see how weird the part of the world that deals with money, how weird they think, and that lives are not important, and then it's just money. It is, yeah, if you get the opportunity to have a little bit of a conversation or talk with the other side, it's worth doing. We think we're all the same as we're all researchers, but there's a scary world out there. Thank you. Go do fun stuff. It's almost dark. I have no idea how to switch off this computer, so we'll just leave it.